Hey everyone, in this video we're going to be talking about spur and helical gears and specifically looking at an example of the AGMA method for stress and strength. We're going to be looking at a design example that actually brings in some thought process into making changes and how we can use the AGMA method to make changes to a gear set. And this video is part of a lecture series on mechanical design 2 and concludes is the last video on spur and helical gears. So we're going to get started with a example problem which is given here, and this example problem is a typical exam design problem that you would get in a mechanical design 2 class such as this one. So we're going to start by just reading through the problem and kind of understanding what the problem is telling us. So we're told that you just got hired by BMW after your predecessor was fired because he did not design a gearing system that followed the following specifications. And his goal was to follow the following specifications: design a commercial enclosed gear drive with 20-degree spur pinion teeth with 16 teeth on the pinion and 48 teeth on the gear. The face width is 5 inches, diametral pitch is 6 teeth per inch. And he made it of grade 1 steel, a hardness of 200 Brinell to number 6 quality, uncrowned, accurately and rigidly mounted, which is very similar to the previous example problem we did in the previous videos, but just highlights what the original terms were for this problem and the way that the original designer designed this problem. The pinion has a life of 5 times 10 to the 7 cycles and a reliability of 0.9. The engine team gives you the specs of the engine. So it tells you that this gear combination needs to be used through an engine, and essentially we're given that the gear or the pinion is going to be rotating at 6,000 RPM at 350 horsepower. Now we're told, using the AGMA methodology, you need to determine the safety factors for your predecessor's design. And you don't need to determine them because you already found them. Okay, so you found them to be SF of P is equal to 0.92, SF of G, so for the pinion and gear, so that's the safety factor in bending, is 0.92 and 1.3. And then for the pinion and gear, for the safety factor in contact, we have 0.64 and 0.65. And we can clearly see that these three values are not okay. Okay, immediately we should note that the safety factors would be too low in order to be designed. And that's why probably your predecessor got fired, for example. Okay, we always need a safety factor, depending on what is given in the problem. We always need SH to be greater than 1 and SF to be greater than 1 in order for our system to work. That would mean that essentially the strength of the gear would be higher than the stress that the gear feels. So we're then told in the question, keeping the ratio of hardness between the pinion and gear equal. Okay, so that means that the ratio of hardness between the pinion and gear is equal. So that means that if we have 200 HB for the pinion, we need to have 200 HB for the gear itself. And assume Yn and Zn remains constant with a change of hardness. So we're told that Yn and Zn are basically going to be constant, okay, if there is a change of hardness. Determine what hardness would be required to achieve an overall safety factor of 1.2 for both the pinion and gear. So what the problem is asking, and we'll write little a here because that's the first part of the problem. And we're going to start with the first part of the problem, then go into the second part. We're essentially trying to find that all of our values for SF should be greater than or equal to, let's say, 1.2, and all of our values for SH should be greater than or equal to 1.2. Now, another way to phrase this problem could have been phrasing using the design factor, but in this case, we're using the safety factor directly. So we know that all safety factors have to be at least 1.2. And so what we're going to do is we're going to have to make changes to the hardness and hopefully get a safety factor that's greater than 1.2. So you would tell me that now, well, we need to start working through finding the sigma and finding all the terms within the AGMA bending equation and AGMA contact equation, then finding SF and finding SH. Now we're already given SF and SH. So we don't need to go through, in this type of problem, we don't need to go through and work through the whole AGMA equation. Okay, and whenever you have a problem given an exam, you will never have to go through the whole AGMA equation. It would take too long, except if you were given all the factors to you already, or most of the factors, and maybe you would have to find one or two factors here or there. Okay, so one thing that's important to do now is to say, well, we're going to change our hardness. So we're told in part A that we can change our hardness in order to increase our safety factor. Okay, and we're told some things that happen when the change of hardness happens, which we'll talk about later as we go along the problem. We know that we have some restrictions that we already talked about. So if we change the hardness, we need to then start looking at our whole system and figuring out what happens if we change our hardness and what terms are going to be modified basically by changing the hardness. So I'm going to put it in green. So I'll put in green, okay, I'll just highlight it in green so that we know what we're talking about. And I'm going to box all the terms that would be affected by hardness. So two terms that would be, so what terms are affected by hardness? So if we look at the bending equation, we can see that none of the terms in the bending equation for sigma are going to be affected. None of the terms in the contact equation are going to be affected. And essentially, the hardness of our material is only going to determine what our safety factor is. Okay, it's not going to determine all of the other terms. So we can see that hardness affects ST and SC. We also know that it affects YN and ZN. If you change your hardness, you could potentially change your YN and ZN depending on where you're looking on the graph and what you have on your graph. Now, we're told in our question that YN and ZN should stay constant if there's a change of hardness, so we're not going to take those into account. Okay, so in order to increase our safety factor, since the change of hardness only affects our bending safety factor, we don't really need to use these equations. Even though we think that we might have to find sigma and sigma c, we don't need to find sigma and sigma c to solve this problem. And we'll see why we don't have to do so. Okay, so let's start with, so we know that we're going to be using the bending safety factor and contact safety factor equation. So let me write those down really quick. So we have them up here. So let me write the bending safety factor first. Okay, and we're going to start with the problem in bending. So we can see that in bending, SF is equal to ST times YN over KT KR, all divided by sigma bending. And I'll add a sigma bending so that we make sure that we know we're sigma bending. Now, one thing that we need to figure out is that we know that in bending, in the problem, we're given that SFP is equal to 0.92 and SFG is equal to 1.3. So let me write that SFP and SFG, and I'm going to add a subscript old to define the original design or the old design. We know that SFP old is 0.92 and SFG old is 1.3. So we see and we know that these safety factors need to satisfy a value of at least 1.2. Okay, so it needs to be equal to 1.2. Now, obviously, we see that this value already satisfies this case. So SFG already satisfies it. However, SFP does not. So we're going to have to modify the pinion we're going to have to modify the pinion hardness in order to find a new SF of at least 1.2 or 1.2. Okay, so essentially what we're going to do is we're going to focus on the pinion because the pinion is a limiting factor. And based on opinion being the limiting factor, we can say that we know that we need to find the HB required for SF is equal to 1.2. Okay, so what we can say is that we know that for the pinion itself, SF old is equal to 0.92, and we know that our SF new or our SF goal, but I'll put SF new, is going to be equal to 1.2. So we need to reach 1.2. So what we can say now is we can now write an equation of SF old in terms of all the different terms that we have in our equation, and an equation for SF new in terms of the different things that we have in our equation. So if we write SF old, we have that SF old, which is the old safety factor, is equal to ST old, the strength old, based on the original hardness of 200, multiplied by YN divided by KT, KR over sigma. And I'm kind of separating these terms together because they're going to be, we're going to have an interesting take on this. So then, same thing with SF new. SF new is going to be equal to, we know it's going to be equal to a goal of 1.2, and ST new is going to be something that we have to find. And we have YN over KT, KR over sigma. Now we know that if we change the hardness, none of the terms that are in these brackets here, none of the terms that are in these brackets are going to change, okay, based on our problem. So we can say that these two terms are constant. And since they're constant between the two different designs, we can make them equal to each other and essentially equate the two equations. So we can write that YN KTKR over sigma is equal to, for example, if I can bring over my ST old to here and my ST new to here, and then I can make those two equations equal to each other. So I would be left with an equation that says that SF new over ST new is equal to SF old divided by ST old. Okay, these two values would be equivalent because of the fact that YN KTKR over sigma is going to be equal to each other. Okay, and then based on that, we can find a new strength associated with our new demand of our safety factor of 1.2 and say that ST new, so just by rearranging the equation, I can say that ST new is going to be equal to ST old multiplied by SF new, or safety factor new over safety factor old. So that means that we can essentially write that the strength new, which includes the hardness, is going to be equal to ST old multiplied by 1.2 over 0.92. Okay, so we have the strength. Now, the strength is not 200 hardness, so ST does not equal 200. HB is equal to 200, but we can go to our equation for grade 1 steel. So if we go to our formula sheet and we go to our equation for grade 1 steel, we see that for ST, grade 1 steel is 77.3 HB, which we know is 200 in the old sense, plus 12,800. So we're going to copy over this formula and write that ST new, or the new strength required to get us a safety factor of at least 1.2, would be equal to 77.3 times 200 plus 12,800. So this is our first term, which is ST old, multiplied by 1.2 over 0.92. And then we can say that this would be equal to 36,861. Okay, then based on this 36 ST1, we can then find the new hardness, or HB new, based on the equation for grade 1 steel with a new HB. So we can say, to find HB new, we can say that 36,861, which is a new strength that we need to get a 1.2 safety factor, would be equal to 77.3 times 200, times HB new plus 12,800. And if we rearrange the equation, we find that HB new is going to be equal to 311. Since the gear old safety factor, so SF for gear old, is higher, we know that 311 HB will satisfy the 1.2 minimum. Okay, so in order to satisfy bending, we would essentially say that we would need, if we wanted a safety factor of 1.2, and we were told that we can only change the material of the gear and the hardness of the gear, we would need at least a hardness of 311. Okay, so we've satisfied, for the problem above, we've satisfied that keeping the ratio of hardness between the pinion and gear the same. So we know that the pinion and gear are going to have the same ratio of, so we're going to increase the gear and the pinion to 311. Then we assume yn and zn remain constant with a change of hardness. Then we have achieved an overall safety factor of 1.2 for both the pinion and the gear in bending. So now we've proven that HB 311 satisfies bending. Now, since we have to satisfy all safety factors, we also need to check that 311, or I can write, does 311 satisfy contact as well? So what we can do is we can do the exact same technique and try and satisfy our contact stress with either 311 or trying to find the number that would satisfy contact. So if the number that satisfies contact, so if we find that HB new for contact is less than 311, then that would mean that we can use 311. So I'll put if HB new for contact is greater than 311, then we have to use HB new for contact. So we always use the higher number between the bending value for HB and the contact value for HB, because we need to satisfy all safety factors, not just the safety factor for bending or not just the safety factor for contact. So we're going to run the exact same technique, but this time in contact stress. So we're going to solve for contact now. So we're going to use that SH old. Okay, so let me rewrite this really quickly. So we have SH sub old is equal to SC sub old multiplied by Zn over KTKR, all divided by sigma C. And I'm going to do the same separation as before. I'm going to separate these terms from SC old. We know that Zn doesn't change. We also know that if we look at our full equation in our formula sheet or here above, we see that the contact safety factor has a CH term. We're going to omit the CH term because we're going to focus on the pinion again. So we're going to focus on the pinion because the pinion is the limiting factor. The pinion has a lower safety factor or a lower SH, therefore we're going to focus on the pinion, just like we did in the gear. So you always want to focus on the one that has the lowest safety factor. And usually that's going to be the pinion out of the two because it has more rotations and stuff like that. So based on that, we know that these values are constants. So then we can write in the same way as before, we can write that SH new is going to be equal to SH old multiplied by SC new over SC old. And then we can solve for, we can then rearrange this equation and solve for SC new is going to be equal to, so one way to write it is to write it in terms of SH new over SH old and go that way, or you can find your SC new based on 1.2 as our goal over 0.64. So that would be our SH new over SH old multiplied by 322 times 200 plus 29,100. And that's the equation for grade 1 steel, for the hardness of grade 1 steel, for the strength of grade 1 steel using the hardness. So we get a value of SC new is equal to 175,312. So I'm taking a couple of shortcuts here because it's the same technique just applied to a different number. And then I can find that my HB, my hardness, HB new is going to be equal to, if I rearrange the equation to find HB, I can say that it's 175,312.5 minus 29,100, all divided by 322 based on the new numbers, and we get that this is 454 HB. So same exact technique. Now, we can also say here that SH of your gear is greater than SH for your pinion, and therefore we can say that the design would be safe for the gear. So the pinion is a limiting factor because of that. And so we can say that the HB required is 454. And that would be our final answer. The reason the HB required is 454 because 454 is greater than 311. So in order to satisfy at least 1.2 safety factor in all the terms, so all four terms above in the question, which are given at the top here, in order to satisfy all the 4 points, we need an HB of 454 in order to satisfy those terms. So we can see that that's what we need to do. Okay, and that essentially concludes part A of the question. Now you can also see that in part A of the question, it tells you you do not need to compute stresses to solve this problem. So whenever you're given a problem like this, you would probably be told not to solve the stresses because you could very well go through the whole AGMA methodology and compute all the stresses and then actually find numbers for SF and SH based on the new ST and SC. But it's not necessary to do so because we're only changing something between an old design and a new design. So we need to get accustomed to the fact that whenever we're making changes to an existing system, we only need to change the terms that are changing in the existing system. So for example, if we decided to change something else, and let's say I looked at these terms right here, and so I looked at the AGMA equation or the bending equation, and I said, for example, that KV would change for some reason because we changed the quality. If we changed the quality of our gear, KV would change, and therefore sigma would change. Okay, now if we have the original value for sigma, saying, for example, sigma is equal to 10,000, we can find a new value of sigma based on the new value of KV. We don't need to compute all the other terms in order to find the value of KV. So we'll talk about that in a little bit after we finish part B of the problem as well, but this is an important point as well. So let me just show this again. Okay, so let's go back to part B of the problem now. So in a second instance, your bosses want you to extend the life of the pinion to 5 times 10 to the 8 cycles. So currently we have a 5 times 10 to the 7 cycles without changing the materials or hardness, but keeping the same safety factor. What changes to the gear set would you recommend be made to achieve this? Please explain your answer. You do not need to calculate anything here, but just explain what would be changed and what influence it has on other factors. You can use equations to help your explanation as well. Okay, so we're told we don't need to calculate anything, but we kind of need to explain what changes we would make in order to extend the life by 5 to 8. So let's talk a little bit about how we could increase the life, and then what would happen when we increase the life and what would happen essentially to our gear set. So part B. Let's write about part B a little bit. Okay, so in part B, we're told that we have a safety factor. So we'll start with bending, for example. Okay, and I believe in the question, so what changes to the gear set would you recommend? So we're going to start with bending, and it's going to be the same thing for bending and contact pretty much. But let's assume that we're looking at bending first. Okay, so if we're looking at bending, we have the equation that says SF is equal to ST times YN over KT KR over sigma. Okay, and we're told that we want to increase our life from 5 times 10 to the 7 cycles to 5 times 10 to the 8 cycles. Okay, and at the same time, we also want to keep SF the same. Okay, so if we have this equation and we highlight the changes that are going to happen by changing from 5 times 10 to the 7 to 5 times 10 to the 8. So the changes that are going to happen due to the cycles, there's only one term that's going to be affected by it. Okay, sigma is not going to be affected by it because sigma is not a function of the number of cycles. The only term that's going to be affected is this term right here, yn. And what's going to happen to yn? Well, yn is going to go down in value. So if we go to our chart and we solve for our chart, we look at our chart here, we have that yn is going to, so we'll go to the yn chart. We see that if we are at 5 times 10 to the 7, so for example, 5 times 10 to the 7 would be somewhere around here, okay? And we then decide to change to 5 times 10 to the 8, we see that there's a reduction in yn, which means that based on our equation that we have, we also have a reduction in SF. So SF, as a result of this, gets reduced, and I'll write it as S sub F. S sub F gets reduced, okay? So that means that we have a reduction in safety factor. So what we need to do is we need to somehow increase we need to somehow do something about our stress, okay? Or we need to do something about our strength. So one thing we could do in order to increase SF again, so because there is a decrease in SF, I'm going to write that we need to counter the reduction in safety factor. Okay, and I'm taking SF as an example, but SH could also very well be an example. Okay, so we need to counter the reduction in SF. So how do we counter the reduction in SF based on our diagram here? So a couple of things we could do. We could change KR, we could change the reliability, but it's not that easy to change the reliability and it doesn't change that much. So one thing we could do is change the reliability, but that's not really a preferred way. But the two things that we can really do are change ST and change sigma. Now, if we go to change ST and sigma, if we go back to the drawing board and back to our question, we're told that we cannot change the material or hardness, and we need to do something else in changing the material or the hardness. So because we can't change the material or the hardness, our ST will not change. So we cannot, due to question, we cannot change ST. So the change that we would have to make is we would have to change sigma. Now, in order to increase our safety factor, what we need to do to sigma, we need to figure out what we need to do to sigma. We need to lower sigma, okay? Now, in addition to just bending, so let's keep doing bending now, and then we'll talk about changing bending and contact as well after. Okay, for now we're just going to keep changing bending. We now need to write the equation for sigma in bending. So I'll put sigma b just so we make sure we don't confuse ourselves. So I'll write that the equation for sigma b is equal to the following. So give me a second while I can find the equation. So sigma bending is going to be equal to WT, K0, KV, KS. And actually what I'm going to do, instead of doing this, I'm just going to copy this again. I'm going to copy all four equations again, just so we have them all. It'll be easier to solve for. So I'm going to copy this. That way we have all the equations available to us to discuss the other terms as well after the fact. So we have that sigma is equal to WT, sigma is equal to WT times KO, KV, KS, P over F, KM, KB. And so now we see that in order to reduce sigma B, we can reduce any of the terms in that equation. If we reduce these terms, or the other way is to increase other terms. So one thing we can do that we can see is if we increase F, so if F gets increased, our sigma B reduces, right? So F is at the bottom of the equation here, okay? It's at the bottom. So if it gets reduced, if it gets increased, we're going to reduce our value for sigma, okay? Another way to do it is to say, what if we lower power? So if we lower the power requirements, okay, which would mean that if we lower the power requirements, WT would go down, because we know that WT is equal to 33,000 times H over V. So if we lower H, we lower WT, and that would also help us solve the problem. Okay, so there's many different ways in which you can solve the problem. So we can affect with WT as well. And then there's other ways to affect it as well, but they become a little bit more complicated. So another way to affect it is to say, so I'll put that this is option 1, option 2, then there's a third option, for example, which is to increase the quality of our gears. So if we increase the quality of our gears, what happens? Well, KV goes down, okay? So if we go really quick to our KV values and looking at our KV overall, so if we go to our KV chart, we can see that the dynamic factor KV, if we increase the quality, okay, so let's say we had a quality of 6 to start with, and we increase the quality to 11, then we would be going from, and let's say the pitch line velocity, I don't know the value, but the pitch line velocity is 1.7, then you would reduce all the way to 1.1 for your dynamic factor. So you would change your sigma dramatically by changing your QV. So this is another way to do it. So there's many different ways in which you can do it, and all of these would result in sigma B being reduced, which would result in increasing your SF back. So what we can say is we would suggest 3 changes. And again, you don't have to suggest all 3 changes in this question. You only have to do one. So you can say 3 changes. change number 1, change number 2, change number 3. Change number 1, which we explained, is face width goes up, which means that sigma goes down, and then based on sigma going down, then that means that SF will increase. Okay, so then that solves our problem of keeping the safety factor the same. The second way of doing this is to say power goes down, which means that our WT, I'm going to write it as W sub T, goes down, which means our sigma goes down, which means our SF goes up. So we've solved our problem once again. And then the third way, which we talked about, is quality. I'll put it as Q goes up, which means that KV or QV, sorry, Q sub V goes up, therefore KV goes down, therefore sigma goes down, which means that SF goes up. So this is just looking at our bending. So this was looking at bending. Now what we can do is we can see if these three changes affect the contact as well. So let's see if they work for contact as well. And they work for increasing SH. So let's look at contact really quick. So if we have contact, and I'll put a blue color for contact right now so that we keep this blue color for contact. So if we have the contact safety factor is equal to SH is equal to SC, ZN, CH for the gear, but we're going to be interested in the opinion, but we'll still write it over KR, all divided by sigma C. We can see that once again, the changes that we can make in order to re-increase, so if we have a lower Zn, so Zn is going to be lower, just like Yn is going to be lower, so you can see that from the graph. Okay, since we have a lower Zn, that means we're going to have a lower SH, and we need to compensate that, and I'll show the compensation in green, and the compensation in green needs to happen from sigma C being reduced. If sigma C is reduced, then that means SH increases again. So what we need to do is modify sigma C. So based on the sigma C equation that we have above, we can highlight it right here. So we have this equation right here. We need to make changes, and we need to see if the changes that we wrote for bending also work for contact. So typically you wouldn't go through all this process to solve that part of the problem. You would just go through a logical step of saying, well, if we increase face width, does it work in bending? Does it work in contact? Yes. Okay, problem solved. Okay, so, but you need to show a little bit of the thought process that you went through. Okay, so given this problem, we can look at if we increase face width, would sigma C decrease? So would sigma C decrease? Probably. So let me copy over the three changes that we made and see if they affect in the same way, if they affect our sigma C as well. And they're obviously going to affect in different quantities. That's why we're not asking you to calculate all these, because it would take a little bit of time to calculate all those changes, but it's a good example of what's happening. So if we increase F, so F is at the bottom of the equation here, so I'm going to highlight it in yellow. F is at the bottom, and therefore that would mean that sigma C would decrease if we have F at the bottom. So we can say that sigma C decreases, and therefore SH would increase again, which is good in order to counteract the Zn reducing it. Now, if we decrease the power, we have the same effect. So the power is at the top of the equation. So if we decrease the power, we automatically decrease sigma C as well. So we can say that sigma C decreases, which means that SH goes up. So it satisfies that. And then quality, QV, same thing. Quality would also decrease sigma C, which would mean SH increases. So all three of the changes that we propose for bending also work for contact. So that essentially concludes the problem and explains how we're doing this. Now, I like using this arrow system to try and understand your system, and then you can write a one or two line description of what happens. One way that If you knew what you were doing and you were to solve this problem based on the question given, then definitely what I would do to resolve the problem. So let's say we had a clean slate and we were to solve for problem B. So let's go back really quick to the part B of the problem. And part B of the problem says, in a second instance, your bosses want you to extend the life to 5 times 10 to the 8 cycles without changing the material hardness and keeping the same safety factor. So we know we need to keep the same safety factor, and we know we can't touch the hardness. So the only thing we can really touch to keep the same safety factor is sigma. So what we need to say in our equation is the following. What we need to start with is say, okay, I know because I'm increasing my life, so since I'm going from 5 times 10 to the 7 cycles to 5 times 10 to the 8 cycles, I know that my yn, comma, zn are both going to go down. Since I know they're going to go down, that means that my safety factor SF and SH are both going to go down. Now, they're going to go down, but we need to keep them the same. So that means that we need to make a change that will increase our safety factor. Okay, so we can say in green, we need to make a change that increases safety factor. And since we need to make a change that increases safety factor, we have two options. We can either look at the strength or the stress. And based on that, we're going to pick the stress because we are constrained in the problem. We cannot use the strength. So we cannot change the strength. One way to do it would be to change the strength and then you're good, you're done basically. But in this case, we can only change the stress. Now, what we know is in order to get a higher safety factor, we need to increase the stress. Therefore, we will decrease the stress through different techniques. And what we're going to do is, as a choice, I would start with this choice because it's the simplest choice, is I would increase the face width, which would decrease sigma C, and finally, it would mean that SF and SH, based on the equations, would increase. And that concludes my problem. So I can write one final part saying increasing face width would increase safety factors in order to counter the increase in cycles. And that's pretty much it, okay? That gives us essentially a fully solved solution to our problem. Now, in the first way I solved it, I went a lot more in depth to try and really explain to you how it works from a theoretical point of view. But this is a much faster way in which to solve it, which took around 5 minutes to be able to solve. And that concludes our content on gears in general. Okay, so we're done with the content on gears. And the next module, we're going to be talking about rolling contact bearings. And we're going to start a completely new subject of rolling contact bearings as well as journal bearings in module 4. So we'll see you in the next module. This concludes module 2.